Okay. So let's start off with the textbook questions. Does anybody have either of these you would like me to go over? Any questions with either of them? So perhaps it would be beneficial if I just explained to you what this is about again, because I think maybe you're looking at it and going, I'm not quite sure what it is we were doing here. I'm not talking about these questions where you have a specific point, where in question 1a that we're looking at here, your limit formula would have the number 2 in for a and the number 3 in for f of a. I'm not talking about that. I'm talking about, in general, determining the expression. So just to set this up for you, I'm just going to set up number 10, and we might even do 10 in its completeness. But we're going to have the limit as h approaches 0. One of the things we learned last week on Friday was that if you want to come up with a general expression for the slope of the tangent anywhere, and by the way, that expression is called a derivative, just so you know. When you want to find the derivative, which is a general expression for the slope anywhere, you have to use this formula. Hold on. But you're not going to put in a specific value of a. So what this literally becomes is, since the function, I'm just going to write it here so I can refer to it, since the function is 3x squared plus 2x, f of a plus h will be 3 times a plus h squared plus 2 times a plus h. So f of a plus h means I'm going to put a plus h into the function wherever there's an x. So it's 3 times the input squared plus 2 times the input minus f of a, which is what I get when I replace every x with a. Of course, remembering to subtract the whole thing. By the way, Enrico, do you remember what the derivative would be here? You remember the rule and what we would get?
6x plus 2.
Right. The expression we should get is 6x plus 2. And if you haven't figured out that yet, don't worry about it. That's just a shortcut that some of us have figured out. We should be getting 6 times x plus 2. The only way for you to evaluate this limit is to get rid of the h on the bottom, because if you put h equals 0 in, which really you're supposed to, that's how you evaluate a limit. If you put h equals 0 in, you'll get 0 on the bottom. By the way, you will also get 0 on the top. Because if I put h equals 0 in, if this is a 0 and this is a 0, then this is 3a squared minus 3a squared. This would be 2a minus 2a. The only recourse here, everybody, and again, you may not like it, is that you have to rewrite this expression by expanding this whole thing out. And I'll double check all of that. Think it looks okay? Yeah. Okay. This is all over h. And it is a royal pain, but yeah, you got to keep writing this limit as h approaches 0. You know what? I don't have any objection to you at this point cutting a little corner. When you cut a corner, that's like cutting across somebody's lot. You're just getting there a little quicker, right? That's where the expression cutting corners comes from. 3a squared minus 3a squared. I don't need to worry about it. 6ah. I don't see any other ah's there. 3h squared. I don't see any other h squareds. I have a 2a minus a 2a, which is gone. This is squared, isn't it? So I've taken care of those. I've taken care of the 2a's. I have a 2h, and this is over h. By the way, if you cut corners like that, you run the risk of making a mistake, right? I can now factor an h out of the top and be left with 6a plus 2 plus 3h. I just switched the order of the three terms on the top to impress on you what I tried to do on Friday, which is that the terms that have h to the power of the 1 are the terms that are going to determine that expression. Because anything that has more than one h in it, when you factor the single h out, you will still be left with some h's. And when you cancel these two, now you're going to put h equals 0 in, and this term will become 0, so you're left with 6a plus 2, which is what we said you should get. Well, we said 6x plus 2, but x is a. So the slope of the tangent here is equal to 6a plus 2. Incidentally, you remember what I just said? I'll repeat it. A is x, isn't it? Okay, so what's going to happen tomorrow is when you come in, we're going to take this formula and we're going to say, well, come on. Who's kidding who? This is what we're talking about. It's not a, it's x. Let's call it what it is. We tend to call it a when we're talking about a specific number, but tomorrow we're going to say, let's drop the pretense of saying x and let's just use a. So all of these a's are going to be x's, all of them. And when you get to the bottom, you'll have 6x plus 2. And that's called the derivative. So does anybody have any questions? Yep.
Can you do B for that question?
Sure. So what we have now in A is we have a formula for the slope of the tangent, which is called the derivative. And rather than writing m of tangent, we've got notation we'll learn about tomorrow. There's lots of ways you can communicate the derivative. Is equal to 6. I'll stick with the a. You guys understand my point about changing it to x, right? It is an x coordinate. Now in question B, you're asked at what point on this function is the tangent parallel to the line y equals 10x minus 2. So there's something else going on here. This is the slope of the tangent to the parabola. Y equals 3x squared plus 2x. And over here, we have the line y equals 10x minus 2. And what we want to happen here, Malia, is we want the tangent line and this line to be parallel to each other. Okay? So, I'm not going to worry about the exact nature of this graph, but there's a parabola here, okay? And there's a line here. Would you agree that this point has a tangent line which is not parallel to that line? Right? This point is not parallel, but somewhere along here, there will be a point so that the tangent is parallel. And what makes them parallel is the slope of this line and the slope of 10x minus 1 are equal. That's why lines are parallel. So if we go back and take a look at this line has a slope of 10, which means the slope of the tangent line has to be 10. But we're so far anyway, we're really used to, let me write this out again, m of tangent equals 6x plus 2. We have always been used to in this course so far of putting in a value of x to find the slope of the tangent. This question tells you the slope of the tangent and asks you to find where the slope of the tangent would equal 10. So if I solve this equation, it's a pretty trivial equation to solve. I subtract 2 from both sides and get an x-coordinate of the point being 4/3. Now we can discuss how far to go with this. I could just answer the question and say it's at the point on the function where x is 4/3. I could go further and find the y-coordinate. In fact, I should probably look and see how it's worded. That's a little ambiguous. At what point? I could answer it by saying at the point where x equals 4/3, but I would be better off putting 4/3 into this function and getting I think 8 for a y-coordinate. Is that right? Okay. Does that answer it, Malia? Okay. Any other questions at all, either from the textbook or the handout? Yeah.
Assignment 1C.
C? So is this the question you're looking at? Yeah. Okay. And in assignment 1, we are asked to use the x minus a and x approaching a deal. By the way, tomorrow we will always be looking at the h formula. So the slope of the tangent will be equal to the limit as x approaches 1 of f of x minus f of a over x minus a. So does that setup make sense to you? I didn't write the formula down, but this is your f of x. This is your f of a, also known as the y-coordinate of the point. You certainly could, and some people will, do the following. But I'm going to erase it in a second. What some people will do is this. Right? There's f of x, and then f of a is putting a equals 1 in, but that 1 over 4 times 1 plus 1 is 1/5. It's already given to you. Now I need to, well, I don't need to, but it's going to make my life a lot easier if I can eliminate this denominator and this denominator. And I can do so by multiplying the numerator of the whole thing by 5 and by 4x minus 1. But if I do that, I have to multiply the denominator of the whole thing plus 1 by both of those as well. And don't forget what happens. I've tried to acclimatize you to this from very early on, that the bottom becomes quite messy. Right? There's all this clutter on the bottom. We've got an x minus 1, we've got a 5, we've got a 4x plus 1. But since your goal is to eliminate the x minus 1, there's nothing in it for us. In fact, it's going to hurt us if you start expanding that whole thing out. So you want to leave it that way. On the top, when I multiply this by this, the 4x plus 1 cancels with the 4x plus 1, and I'm left with the 5 and the x. When I multiply this by this, the 5's cancel, and I'm left with 4x plus 1, which I'm subtracting. But, and it's so common, right? You got to remember to subtract that whole thing. The top becomes, I'm being a little lazy here, but this becomes x minus 1. Right? 5x minus 4x is x. And then we have we have negative of 1, or we're subtracting 1, so we get minus 1. And now this cancels. And again, it isn't that I'm not showing all my steps. The problem is when you start doing this, you can make errors. I'm just pointing that out to you. It's better to rewrite it. But I'm just in teaching mode here. So what we're left with is 1 over this. And now I can go ahead and I can put in for x 1 and get 1 on the top and 5 times 5 on the bottom. So the slope is 1 over 25. And I can't remember. Short-term memory problem or something. I can't remember. I believe on Friday I said, don't worry about the equation, but just as long as we can get the slope. Is that good? Okay. Enrico? 2g. 2g. So this is the h formula, and we have 5 over 4x cubed. Well, that's weird. Give me 1 second. That was weird. Okay. Y equals 5 over 4x cubed. Correct?
Yeah.
Okay. So we are going to have the limit as h approaches 0 of f of a plus h. I'll tell you, I'm not really looking forward to the prospect of multiplying a plus h times a plus h times a plus h. But we may have to. We might be able to avoid and, weasel and maneuver our way around that idea, but we might not be able to. Minus that all over h. And again, that a tomorrow is going to become x, and I almost wrote x instead. It really doesn't matter, does it? So I have a denominator that is a real trouble. Like I've denominators that I don't want. I have 4a plus h cubed and 4a cubed. So I'm going to do the same thing that I did with the previous question, which is to multiply by 4 and a plus h cubed and a cubed. I don't need everybody to multiply by 4 twice. I mean, I could, but then I'd get extra 4s everywhere. It's not going to affect the answer. And then on the bottom, I'm going to have 4 and then a plus h cubed and a cubed. This will give us the limit as h approaches 0 of, so when I multiply this by this, I'm going to be left with a cubed. The 4's cancel and the a plus h's cubed cancel, so I'm left with a cubed and the 5. Okay? And I can start to see right away that we're not going to have to FOIL out a plus h times a plus h times a plus h. I'm thinking we're going to have a difference of cubes. When I multiply out this and this, the 4 and the a cubed cancel, and I'm left with 5 times a plus h cubed. And of course on the bottom I've got this mess. And I know I keep moving these things on the bottom around to different places, but it doesn't matter where they are. Okay, I've got an h, I've got an a cubed, I got the 4, I have the a plus h cubed. So now what I'm going to do, Enrico, is I'm going to factor 5 out of the numerator. being left with a difference of cubes. I'll show you what that looks like. You probably wouldn't do this in post-secondary on an assignment you're turning in, but I'm just going to figure out what that top is equal to on the side. You really should rewrite it each time. I can factor out a 5 and be left with, oh, I already did that. So that 5 is there. Now, what I'm going to have, I didn't leave myself enough room, I don't think. I'm going to have, I'll rewrite it just so you can see it as a difference of cubes. When you have first thing cubed minus second thing cubed, it factors into first minus second. And then you also have first squared plus first times second plus second squared. Just squeaked in. Does that difference of cubes ring a bell?
Yeah.
Okay. And the important part here, Enrico and everybody, is that this is negative h. It's a minus a, which is nothing, and then you have minus h, which is negative h. So the top becomes, now I'm going to go back to the actual question, the top becomes 5 times negative h times a squared plus a times a plus h plus a plus h squared. And the bottom, it's been a while, but I'm pretty sure we had a 4, an a cubed, an h, and an a plus h cubed. Is that what we had? Pretty sure. The h, of course, cancels. The h, of course, cancels, leaving a negative, which I'm just going to put on the 5. And now we can put 0 in for h. And what I get is negative 5 times a squared plus a squared plus a squared over a cubed times a cubed and a 4. So this is a squared. When h is 0 here, this becomes a times a, which is also h squared, or a squared rather. This becomes a squared. Are you good to there? Yeah. So what we have 3 a squareds on the top. So I have negative 5 times 3a squared over 4 times a to the 6. I add the exponents when I multiply. And when I'm adding like terms, it's like adding cats. 1 cat plus 1 cat plus 1 cat is 3 cats. So I get negative 15 over 4, a to the 4. So I'm taking a squared divided by a to the 6. Can you tell me something? So we're done. And you notice what I did here? I didn't put the value of a in, did I? But you and I have been talking about that. You're fine with that, right? You could have put a in. I'm already thinking about doing the stuff we're going to do tomorrow. I didn't put the number in. You could have put the number a in from the beginning. But you should be able to follow this. Now, just a second, though. What was the function? Was the function y equals 5 over 4x cubed? Would you agree that's the same as saying 5 quarters x to the negative 3?
Yeah.
If I take that exponent and multiply by 5 quarters, I get negative 15 quarters. And if I subtract 1 from that exponent, it becomes negative 4. Works with negative exponents too. Right? Remember how you took the 3 times the 2 and then you dropped 1 from the exponent? Works here too. Won't always work, okay? But it does a lot of the time. Again, I got really caught up in what we're doing tomorrow that what was the actual coordinate point?
1, comma, 5 over 4.
So you would have had 1 plus h and then 5/4. You wouldn't have had all those a's. But you should still be able to follow what I did. We're going to move on now. We could do more and more and more of these, but I think it's time to move on. And we're going to be doing some more limit work today. Tomorrow might be the last day that you actually have to do. You have to use limits to do these problems. Okay. So we're looking at rates of change here today. This is an application unit. We're going to be calculating and determining and interpreting average and instantaneous rates of change. And we're going to be relating average rates of change to the slope of a secant line, which we've learned about. And you're going to be learning that the slope of a tangent line refers to an instantaneous rate of change. Don't forget, a rate of change is a measurement of a change of one thing with respect to another. 12 chicken wings per hour. $150 a day. 12 kilometers per hour. And most rates of change are measured with respect to time, but we're going to be looking at least at one example today where the x variable is not time. It could be something else. To begin with, when a ball is dropped from the CN Tower in Toronto, the distance fallen after t seconds is given by that formula. So big shock to you physics people. We do not use d for distance in math. We use s. You're just going to have to get over it. We don't use d for distance. We use s. D has a special meaning in calculus. So the position or the distance that it falls is equal to 4.9 t squared. This is just function notation, which says the distance depends on the time. And the other thing for you physics people you need to understand is you cannot use kinematics formulas to solve math problems. They don't always work. So you may be tempted to go, oh, I'm going to use Vf minus Vi over t equals acceleration, and I'll use 9.81. That might not work, okay? So those kinematics formulas are kind of useless. What is the average speed of the ball as it's falling from 2 to 5 seconds? So we define average speed here. We define average speed as being a change in position over a change in time. And we are not picky in math at all about using vector symbols. If you don't know what I'm talking about, then you don't need to worry about it. So what does a change in a position mean? What it means in this specific example is that we need to take the position at 5 seconds and subtract the position at 2 seconds. That's the change in the position. So whatever s of 5 is, we have to subtract s of 2 over 5 minus 2. I want to point out to you that what we've done here for average speed is we've said it's s of t2 minus s of t1 over t2 minus t1. That's what we're doing. And what s of t2 means is the position or distance at t2. This becomes really a pretty simple question. Because you have the formula here, 4.9 t squared, we can write that the average speed is 4.9 times 5 squared minus 4.9 times 2 squared over 5 minus 2, which is 3. Quite frankly, I should have just written 3, right? So it's literally a matter of you taking your calculator out and calculating what this works out to be. If you calculate it in one shot, obviously you have to have brackets around the top when you divide by 3. Callie, do you have an answer?
34.3.
34.3, anybody? And was it 34.3 and that's where it ended? Okay, so the answer is 34.3. And it's meters per second because the top was a change in position in meters and the bottom was a time in seconds. All that means is that's the average speed. And that's a difficult thing to explain to you what average means. It may mean the final plus the initial divided by 2, and it does in this case, but it doesn't have to in all cases. What it really means is if this is the position at the 2-second mark, and this is the position at the 5-second mark, then even though the object was accelerating, if the object went from here to here at that constant speed, it would take the same time as it really took. That's what it means. So now what we're going to find is the instantaneous speed. Well, what I'm going to show you is something that we're not going to do every time. But if you were to take a look at the position as a function of time graph, it's a fairly basic parabola. And we want to find the speed at 2 seconds. And again, you're not going to do this every time. But the speed on a distance time graph is the slope of the tangent. That slope of the tangent is equal to the speed at 2 seconds. So if we take some other point, I'm going to call it x2 this time. I could call it a plus h. I could call it x. I could call it a lot of things. And I consider the secant line. The m of the secant is not equal to m of the tangent, but we're back where we started. The slope of the secant will approach the slope of the tangent when x2 approaches 2 seconds. And how we do this typically with instantaneous speed is we write the following. We say that the slope of the secant is the rise, which is f of x2 minus f of x1, over the run, which is x2 minus x1. I hope it's not lost on you that this 2 seconds is x1. Okay. So this formula that I'm developing here for the slope of the tangent is kind of a hybrid between the thing we were doing with the x approaching a thing and something else. The slope of the tangent would be equal to the limit, give myself enough room here, equal to the limit as x2 approaches x1 of the slope of the secant. And you know, I wish it wasn't this way, but you know what I'm telling you is there's 3 formulas for the slope of a tangent. There's the one on page 22 of your handout that says the limit as x approaches a of f of x minus f of a all over x minus a. There's the one which I believe is on page 23 of your handout, the limit as h approaches 0 of f of a plus h minus f of a all over h. And there's this one. But I hope you see that if I change this and this to a, and I don't even label this x, I just say x, it's the same formula we've looked at, right? X is approaching a. For some reason, when we talk about applications, we like to use this version. Okay? So, the answer to this question will be v equals the limit as x approaches, now I can use this specific formula with this notation or not, 2. If I had my way, I wouldn't even shown you this formula, but you're going to see it in your notes and in your textbook. So you're going to see it in post-secondary. Of s of x minus s of 2 over x minus 2. We're just finding the slope of a tangent. And you know, if you wanted to, you could use the h approach here. So what does this become? It becomes was it 4.9 t squared? Now, check this out. I am not going to figure out what 4.9 times 2 squared is. Because I can take the 4.9 out and then just factor the difference of squares to get my x minus 2. And I realize right now as I'm talking, in this context, in this question, and I will change it for the next one, all my x's could be t's, right? They're times. So this could be f of t1, t2 minus f of t1 over t2 minus t1. It depends on what you're talking about. You don't have to do that, though. So if I factor out a 4.9, I'm left with t squared minus 2 squared, which is the difference of squares. Now I got t, jeez. X squared minus 2 squared, and it's over x minus 2. So that x squared minus 2 squared factors into x plus 2, x minus 2. And everybody, if it was, the time was approaching 11 seconds, this would be an 11 and this would be an 11, and we'd have 11 squared and 11. So it would still factor into x plus 11, x minus 11. In fact, if the time was approaching a, you would have left x squared minus a squared on the top over x minus a. It's always going to factor. So the limit as x approaches 2 of 4.9 times x plus 2 times x minus 2 over x minus 2. You know what's interesting is I'm doing all this work and I never did what I've taught you to do when you evaluate a limit, which is to put the variable value in to begin with. Right? I never actually put 2 in for x, but you know slopes of tangents don't work that way. You always have to do some work to make it work. X plus 2 times 4.9 is all we have left. Go ahead and put 2 in. So 4.9 times 2 plus 2, which gives me 19.6, I believe. Yep. So 19.6 meters per second. We've talked about instantaneous rates of change before. That doesn't mean that it's even traveling for a second. It means at that instant, that's how fast it's going. If it had a speedometer on it, that would be the reading at that point in time. Yep.
Couldn't you just like put this into 4.9 t squared? Put 2 into that and got it?
No, and the fact that you mentioned that tells me I should change this question. That is a fluke. This happens to be the case. Wow, what a bummer. This happens to be the case where the distance it falls during 2 seconds happens to be equal to the speed that it has at the 2 second mark. But it won't always be. I never noticed that before. I'm going to go back to what Enrico discovered, which is that if position is 4.9 t squared, that means the slope of the tangent should be 2 times 4.9, right? I'm moving this exponent down, t to the 1. And it turns out that 2 happens to be a number that makes this thing equal to that thing. Okay? But if it were 3 seconds, the correct answer would be 29.4, which is what we get when we put 3 in there. But if you put 3 in here, you don't get 29.4. It's a fluke. But I'm going to change my notes so that nobody else notices that. Okay. Have I answered your question?
Yes.
Okay. The above example illustrates this formula, which I've already explained to you. This is how you find the slope of a secant. It's an average rate of change from one point to another. If you want to find the slope of the tangent, then you better take a limit of that as x approaches that particular time or number. All right, let's take a look at a different example. The displacement of an object, position in other words, is given by 2t squared minus t. What's the average speed from 2 to 5 seconds? Okay, so that would be s of 5 minus s of 2 over 5 minus 2. And determine the instantaneous speed at 3 seconds. There's nothing special about the 3 seconds here. It's just a number. It has nothing to do with the 2 and the 5. It's just a particular time. Would be equal to the limit as t approaches 3 of 2t squared minus t. I better not do that. Of s of t minus s of 3 over t minus 3. Let's deal with the average speed first. This is literally just a matter of you putting 5 up here and 2 up there and calculating them. So I get for s of 5, 45, but please check my work. S of 5, I get 45. And for s of 2, I get 6. Are we fine with that? And it's over 3 seconds. Well, that works out to 13 meters per second, I think. I get 39 on the top, 3 on the bottom. 39 divided by 3 is 13. This one is going to be a little more work. S of t is 2t squared minus, check it out, t minus s of 3. Let's calculate s of 3. I don't want to put 2 times 3 squared minus 3. Let's actually calculate it. That's 18 minus 3 is 15. Over t minus 3. Now here's the beautiful thing. And again, I am serious. I find some beauty in the mathematics of this. That top has to be factorable. And it doesn't matter what time you picked for the question. 3 seconds, a millisecond, 1.8 seconds. The result has to be factorable because the t minus 3 has to cancel. And what that means is as you're rolling this around in your brain trying to factor it, I would say to you, don't. There has to be a t minus 3, which means the other number has to be a positive 5, and the other piece has to be 2t, because we want 2t squared, and we want negative 15. If you FOIL that out, you're going to get the quadratic that we started off with. And again, I sorry for going on and on about this. Had this number been 5, we would have got a different number here. But t minus 5 would have been a factor of the result. If it was 1.73, we would have got a different number here, but this still would have been factorable, even with a goofy number like 1.73. These cancel. Now we can put 3 in, which gives us 2 times 3 plus 5, which gives us 11 meters per second. Was this the formula? Not everybody's getting this every time. I know there's some people that are still looking at this, but do you agree the slope of the tangent is 2t minus 1? 4t. 4t minus 1. And what's the time? 3. 4 times 3 is 12, minus 1 is 11. Like, eventually what's going to happen is you'll get to the unit exam and you'll see, oh, find the instantaneous speed. You will not want to use limits. You won't. You'll just use what's called the derivative. All right. If I can get this thing going. There we go. Example 2. A balloon is being blown up. It turns out that the volume of the spherical balloon is equal to 4/3 pi r cubed. Determine the average rate of change of the volume with respect to the radius as the radius changes from 12 to 14. Well, that average rate of change will be equal to the volume at 14 minus the volume at 12 over 14 minus 12. It's not x, it's not y, it's not position, it's not time. It's volume with respect to radius. This is delta volume over delta radius. Which would give us 4/3 pi times 14 cubed minus 4/3 pi times 12 cubed over 2. Now, we want an exact value. Okay, we want an exact value. We don't want a bunch of decimals, which means we should write this as 4/3 pi times 14 cubed minus 12 cubed over 2. We don't want to mix that pi in with stuff. All I did was I factored the 4/3 pi out of both of those terms, and I'm left with 14 cubed minus 12 cubed, and then it's over 2. So we need to figure out what 14 cubed minus 12 cubed is. I've got no earthly idea. 1016. Okay. So that means we have a 4, a 1016, and a pi on the top. And on the bottom, we have 3 times 2, which is 6. And now it's up to us to, figure out what this is in lowest terms. 2/3, 2. I want to say 2032 over 3. Okay. So the answer is it's 2 2032 thirds pi. Now, what are the units? Well, it's a rate of change of volume with respect to radius. The units are centimeters cubed per centimeter. And you don't want to cancel a centimeter. You want to leave it so that it tells you the volume on average in that change is changing by that much centimeters cubed for every centimeter of radius change. By the way, if we work out what that number is, it's going to be very close to 2032. I mean, not really close, but pi is pretty close to 3, right? So I don't know, you're going to get 2100 or something. It doesn't matter. You'll get a number. Okay, let's take a look at the next one. What's the instantaneous rate of change at 13 centimeters? So you'll notice I don't have notation for this yet. I don't have notation for the slope of the tangent. You'll learn that tomorrow. It's called the derivative notation. Will be equal to the limit as the radius approaches 13 of v of r minus v of 13 over r minus 13. So what is v of r? Well, v of r is 4/3 pi r cubed. Limit as r approaches 13 of 4/3 pi r cubed minus 4/3 pi 13 cubed over r minus 13. So what I would like you to do is look at that argument for the limit, the thing we're trying to find the limit of, and ask yourself, what strategy are you going to employ to get rid of that r minus 13? A fatal mistake here would be to calculate what this is. If I factor 4/3 pi out, what am I left with? R cubed minus 13 cubed, which factors as the difference of cubes. One of those factors will be r minus 13. It always works. It's always going to be factorable. So we have the limit as r approaches 13 of 4/3 pi, and then we have r cubed minus 13 cubed over r minus 13. And now we can go ahead and factor that difference of cubes to get the limit as r approaches 13 of 4/3 pi. I'm just going to write that 3 on the bottom. Rather than writing 4/3 pi on the top, I'm going to go 4 pi over 3. I also have an r minus 13 on the bottom. So the difference of cubes is a cubed minus b cubed equals a minus b. A squared plus ab plus b squared. That's where I'm getting this factorization. That's where I'm getting this factorization from. So the r minus 13 is gone. Now can we put 13 in? Sure. We get 4 pi on the top. I don't know if you've noticed this. When this happens with differences or sums of cubes, the trinomial is always 3 equal pieces. It's going to be 13 squared plus 13 squared plus 13 squared. So what do I have? I have a 4 pi, I want to say 507 for the 13 squared plus 13 squared plus 13 squared over 3. I don't even know why I did that. 13 squared plus 13 squared plus 13 squared divided by 3 is 13 squared. Right. So what you end up with is 320, 338, 660, 676 pi. And again, it's centimeters cubed per centimeter. And that's it. We're not going to do the last example. You know what? There's nothing special about the last example. It was a bit of enrichment. We were going to use the graphing calculator for some things. So we're not going to do that example. But that means that your assignment, hate to tell you, is probably going to be a little shorter because you guys are okay with that? Because it won't include questions that come out of that last example. Nope, you're good. You should be able to do these. What are the numbers? Caden, can you read the numbers off for me?
1A, and then it goes...
Just the numbers. One.
Just 1, 2, 3, 6, 7, and 8.
3 to 7. Okay. So just do 1, 2, 3, 6, 7, and 8. 1, 2, 3, 6, 7, and 8. Didn't you say 3 to 7? Was that what it said?
It said 3, 6, 7.
So omit 6. That's good enough. 1, 2, 3, 7, 8. Of course.